According to Britannica, in 1895, a French mathematician named Henri Poincaré published Analysis Citus. This work, along with others from the previous century, such as Leonid Euler's solution to the Königsberg bridge problem, would evolve into the branch of mathematics we call topology.
Brain, what the hell is topology?
Well, I'm glad you asked. Topology is a study of mathematics that focuses on the continuity and geometric properties of spaces. Now, I know that might sound like a lot, but it's fairly simple. Let me give you an example. Take this rubber band. You see how it looks like a limp circle? But watch this. Now what is it? A square? A squircle? Or is it still a circle, pretending to be something else?
Unlike geometry, where shapes are rigid and concrete, topology uses shapes that are more elastic, like a rubber band. These shapes can be stretched, or dare I say, morphed. In the case of a rubber band, we can change its shape over and over again. This would mean our rubber band is homeomorphic to whatever shape we change it to. There are, however, some shapes that a rubber band is not homeomorphic to. For instance, take a look at these scissors, the frames of these glasses, and this can tab. What do all these objects have in common? Pause the video to think about it. To the keen-eyed among you, you may have noticed that these scissors have 2 holes. These glasses have 2 holes, and this can tab has 2 holes. And a rubber band only has 1. And because a rubber band only has 1 hole, and this can tab has 2 holes, they are not homeomorphic to each other. In no way can we legally give our rubber band 2 holes. Even if we were to change our rubber band to maybe look like it has 2 holes, like this in a figure 8 pattern, it would still only have 1 hole. And even if we had a can tab that was elastic, we couldn't make the rubber band and our can tab identical without tearing our can tab or welding on our figure 8 together. Now take a look at this rock. How many holes do you think it has? The answer? 0 holes. This rock has no holes. Therefore, it is not homeomorphic to either our rubber band or our can tab.
Now let's talk about continuity. But in order to do that, let me introduce you to the Mobius strip. And no, it is not a cut of steak. It's fairly easy to make. Just take a long strip of paper, flip one end of it halfway around, and connect the 2 ends like so. Now let's imagine that I ran my finger over the edge of the Mobius strip. I could do so forever, and therefore it would be continuous. But let's say I didn't like the Mobius strip. I just liked the strip. If I were to run my finger over this, I can go, and it would end. And our strip is not continuous. Also, let's imagine I compressed this Mobius strip to such a point that it no longer had a hole. In this case, it would also no longer be continuous. And those are some of the basic concepts of topology. The actual math behind it looks terrifying, yet kind of beautiful. But who are you? And for that matter, who am I? Are we the same person as we were just 3 minutes ago? What about a week? Are we all morphing into our future selves? And more importantly, are we turning into our parents?
Half of our DNA is given to us by our parents. And since our appearance is affected by our genetics, by our DNA, we are indeed becoming our parents. And while genetics are important, the people we hang out with, the music we listen to, and our culture ultimately decide who we become. Our personality, if you will. And adjusting our behavior to match those in a group, fitting in, if you will, is called conformity.
And if you think about it, we're all slowly morphing into our friends, our family, our environment. So, are you what you eat? Technically, yes. The food we eat contains nutrients that our bodies use to grow and mold. But sadly, we don't turn into the food we eat. Instead, the food turns into us. You've probably taken a science class that went over physical and chemical changes. In case you don't remember or you haven't learned it yet, physical changes are changes to an object, like bending or breaking, that are usually reversible. However, chemical changes are changes that chemically change an object, and are generally not reversible. Examples include
Eating food or making cookies.
It seems hopeless. But is there a way we can shapeshift? I mean, is there a way we can make our appearance mimic others? Just like that. Right now, no, I can't think of anything realistic or effective. But who am I kidding? All this shape-shifting, morphing stuff, it's a bunch of hoopla. Science fiction. Right? Charmeleons can change their skin colors to match in with the environment. Do you know what else charmeleons can do? Regrow their tails. A smack is a group of jellyfish. Turritopsis dohrnii is a species of jellyfish that is considered immortal because they use something called transdifferentiation, where one cell can turn into a new type of cell. In humans, we have something similar to transdifferentiation: stem cells. According to Stanford Medicine, stem cells are a special type of human cell that can grow into other types of human cells. This could be heart cells, brain cells, and muscle cells. But they all start off as embryonic stem cells, which later develop into their specialized cell types. As of now, stem cells are somewhat of a mystery, but they have the potential to cure diseases such as Alzheimer's, paralysis, and rheumatoid arthritis. Here's something to think about. Say I was able to replace all of your DNA with mine. In say 10 or so years, would you ever look like me, see like me, sound like me, or see the world like me?
While the idea of shapeshifting is cool and all, we don't really have the medicine or technology to really pull it off. However, topology has some other cool uses. Instead of shapeshifting us, what if we shapeshifted just plain old matter? Shapeshifting the structures of compounds, for example, could make impacts in material science. These compounds could help make more durable plastics for shopping bags, or a sturdier graphite for pencils. A way we can create these materials is with knot theory. Veritasium has a great video demonstrating knot theory, and I highly recommend checking it out. Link in the description. But knot theory is what it suggests. It's the study of knots. All of the knots. So far, and if Wikipedia is to be believed, more than 6 billion knots. With knot theory, we can also tie atoms together with strong knots to make stronger materials. Knot theory can also help us understand proteins, such as this one. And if we can understand these massive, complex proteins, it can mean progress in treating diseases and developing medicines. We also have topological insulators, which could revolutionize electronics as we know it, potentially creating incredibly efficient computers and quantum computers. You may have noticed that normal computers generate a lot of heat when under large loads, such as playing video games or working on large video projects. But with topological insulators, our computers could theoretically produce zero heat, not only making them more efficient, but also faster. And if topological insulators can improve quantum computers, they could also improve artificial intelligence. And if artificial intelligence ever becomes powerful enough, it could potentially shapeshift into you. If AI could shapeshift into us, there's a good chance we wouldn't be able to tell who is who, what is real, and what is fake.
Either way, topology can help us create technology, medicine, and materials that could one day improve all of our lives. Heck, one day we may be able to really shapeshift. Anyways, thanks for watching.